Good day everyone, I hope you are doing fine from wherever you are watching this video. This is going to be a quick tutorial on how to simulate a contaminant transport using COMSOL. So we are trying to simulate contaminant transport in a porous media soil. Just imagine a company reached out to you and you're supposed to design a mine tailing pond. And one of the reasons why they are giving you that design is because the soil stratigraphy of that area has an aquifer below it. Therefore, they want to limit the quantity of the contaminant chromium leachate that is going to leach into the aquifer for a certain period of years. So in this conceptual model, it looks like 2D. So we are supposed to simulate it like 2D, but just as a start, we can idealize it back to a 1D. So I've actually carried out the analysis using my spreadsheet, and maybe I've been able to determine the depth of the pond for the leachate. So let's assume it's going to be just 1 meter and the underlying strata is going to be 29 meters. This is the governing equations that is going to govern the contaminant transport. From the equation, this is the differential coefficient. This V and this second part of this equation is the advective part of the equation. And this third component, the R, is the retardation factor. Usually contaminant can get sticky with soil. And the full component of this part is considering the tortuosity of the soil. So it's the mechanical dispersion where you are considering the alpha, the V, the seepage velocity, and the diffusion coefficient together. So let's go to COMSOL and see how we can simulate this in COMSOL. So when you open COMSOL, this is going to be the first interface. You're going to select your model wizard. We are trying to do it in a 1D. And what we are using is transport of diluted species in porous media for the contaminant transport. And we are also simulating it as a saturated condition. So we'll be using Darcy. So I'm going to add that first. Then I'm going to click on Darcy law. If you want to simulate it in on saturated domain, then we can add the Richard equation. So these are the two we'll be using. I'm going to click study, and it's going to be a time dependent. We are not doing steady state. It's going to be a transient study. So you're going to click done, and you're going to wait for a while to load the interface for the modeling. So this is the interface is going to bring. So the first thing is we need to draw the geometry. To draw the geometry, you can actually drop this down. You can right click and click interval. So it's a 1D, and for the interval, you're going to be having 29 meters. 29 meters. So you can click build selected. So you can see it here. That's build the soil column that we have here, which is 29 meters. That's what we just built. And the next thing is we're going to go to our transport diluted species in porous media, and we're going to input some of the properties we have already. So here it's telling you that, oh, there's going to be convection and mass transport. This is the discretization we're using linear. I won't talk much about this. For the equation, just to confirm, so the equation I'm showing you from Lico's paper here that governs the contaminant transport, that's the same thing we've selected here. But here we have more than that. We have sorption and some other things, but those ones are assumed zero in our simulation. So let's go to the porous medium, go to fluid. So for fluid, we are going to select total dancing velocity because it's a coupled simulation. We are coupling water flow with contaminant transport. So that's where we are selecting dancing for the velocity. And for the source, you're going to leave it as material, fluid material none. So for the diffusion coefficient, let's check our parameters. So we're going to be using 6 e raised to power 10 for diffusion coefficient. So we're going to be using 6 e raised to power 10. That's our diffusion coefficient. And for effective in this one, I just want to make it no correction. Maybe in other videos I can explain the effect of that. So that's just talking about how to consider maybe the tortuosity in soil material. So our porosity user defined, let's make it zero point 0.3. And so in this case, we are yet to add our dispersion coefficient. So you have to right click here and add dispersion. There's absorption, but we're not simulating absorption in this case. For the absorption, we are going to connect it with our contaminant transport and checking the value we have for our mechanical dispersion 8.84 to the power of -8. So you have 8.84 to the power of minus 8. So no flux. So currently it's saying there won't be flux at the top boundary and this is the bottom boundary. But we are going to override that by right clicking here and saying at for the top boundary, we are going to be using concentration because we have a concentration that is going to be leaching from the top boundary. So we are going to click on concentration. So the concentration in our case is 1000 milligram per meter cube, but in terms of mole per dm cube, it is 0.0193. So I can just copy that since I've converted it and just paste it here. So we are going to select that. Oh, that's going to be the concentration at the top. And at the bottom is going to be outflow. So we are going to override it and click outflow. So next thing is to move to the initial value. So what's going to be the initial value in that soil column is going to be 0. So we are done with the transport aspect. We need to go to the Darcy aspect. So we are going to include gravity effect. And next we go to the porous media. So for our storage mode, we are going to select this. Assuming you are simulating maybe unsaturated or some other things, there's a way you can change the storage media, but we leave it as density and porosity. Go to our fluid. The density user defined, we are going to make it just the default values. We are going to go to the porous matrix. We are going to make it user defined. We are using 0.3. And the permeability, we are going to select our hydraulic conductivity, and that is 1e to the power of minus 9. So our hydraulic conductivity is 1 times 10 raised to the power minus 9. So it's going to ask us about the boundary condition. So it's saying no flow, no flow here, but that's not our case. So we're going to right click here. For the down aspect, you're going to go to hydraulics and we can use prayer head. So for this prayer head, first one, we can make it 1 and we click here. What we are trying to say here is from the conceptual model, just assuming we are digging just 1 meter for the pond. So that's like a prayer head of 1 meter on the soil column. So that's why we make it 1 meter. And we are going back to here and select another prayer. You can select prayer head or atmospheric gauge, but in my case, I like to use prayer head. So we can just put prayer head at the bottom and we make it 0. So that means we are just saying it's open to the atmosphere for flow. So it's going to ask us for the initial condition. I'm going to make it prayer head 0. 0 means it's saturated. Think for this, okay, because I didn't click here, okay. So everything is set now. The next thing is to do our meshing. We can just make it fine bits and we're going to build up. And the next thing is go to study and we can compute. So for computing that, we can check our results. This prayer, this is the concentration. So I just computed that without actually setting the time. So I might need to just go again. So let's change the time to annual. So let's imagine we want to compute it for 100 years and see how much contaminant is going to be transported in 100 years. So I'm going to go to study again and compute. The first computer I did was in seconds. It was very small. So now this is the concentration. So, but to be able to relate or visualize our result better, you can go to results and right click, do a 1D plot. You right click on the 1D plot, do a point graph. So we can select here, we can select the expression that we want to, is showing that it is concentration, and we can click plot. So from here, we can see how the plot goes. So based on our parameters, this is the concentration. So we can convert all these values back to microgram or the limits we are dealing with and know how many years it's going to take for that concentration to reach. Another way I do this sometimes is for you to be able to relate with the data, you can go to the derived values, right click, point evaluation, and under here you can select, go to transport media, species, let's use species, concentration, So, and we can click evaluate. Oh, I didn't select. After I click this, I'm supposed to select at the points I want it to evaluate, and I can click evaluate. So those values you see in the plot are same thing here. If we go to the plot, we are seeing about 0.017, and that's same thing you are seeing here about 0.017. So in this case, you can actually copy this value, copy column to clipboard, and you can go ahead in your Excel and paste it in your Excel, and you can convert it to any value you want to work with in your Excel and actually plot your graph. So in this case, I can paste it, and after pasting it, if I want to convert those mole per centimeter cube to mg that I inputted initially, I can just click equals to the converting factor is this, and I can just double click. So I can see I can change it from scientific to general, so I can see how much is going to be transported in the certain number of years based on my parameters. So this is how to simulate a contaminant transport in porous media using COMSOL. If you have any question, you can ask in the comment section. Thank you for watching.